hope you are taking the time to study old quizzes. Okay, I think that is important. It is important if we go back to our learning strategies here from the Make It Stick book. Let's remind ourselves of those. It's a good point in the semester to think about this. We're a little bit past halfway through the semester. You want to practice retrieving things, which does mean looking at old quizzes and rethinking about them and trying to re-answer old questions without looking things up, doing your best, or looking at what the answer is, maybe having a friend quiz you. Practice retrieving things from memory. That does also include something I haven't quizzed you on yet. I might have quizzed a class in the future, but I haven't quizzed you guys yet on the Poisson distribution formula. Probably that will come up on the next quiz, and that's kind of a tricky formula. It involves the number e. So that's something to make sure you study for next time. That's probably going to be on the quiz next time. So practice retrieving from memory. Space out your practice. Again, don't just repractice something an hour later. Wait a day or two, and then practice again. It'll make it a little harder to remember, but because it's harder to remember, you'll have to work harder at it. And therefore that'll strengthen the brain connections better. Interleave your different types of problems. I think that's especially important in statistics, especially coming up to the second exam. Because in the second exam, one of the big things people have difficulty with is understanding what kind of situation we're dealing with. Is it a proportion problem or a mean? Or is it comparing proportions or comparing means? We're going to have all those types of problems on the second exam. And if you don't interleave your studying, it's probably going to make it more difficult on you to decide what type of problem it is, and therefore what type of formulas to use. Have good attitudes, including embracing difficulties. Just make sure you take the time to resolve them. Avoid illusions of learning and understanding. When you just read something and say, yeah, I guess I get it, that's not good enough to me. Right? You should know that by now, especially in math. You read the book and you say, yeah, that makes sense. It doesn't mean you're going to be able to solve a problem. Saying something makes sense when you read it and solving a problem related to it are two pretty different things. I mean, you got to do one before the other, but it's much harder to solve problems. So don't think that just because you understand what you read, that means you fully understand something. Have a growth mindset. Nope. You may not get the grade you want, but try to grow. Try to learn. That's really the key. Get beyond learning styles. Everybody says they have their own learning style, but really everybody should try to learn in every way possible. Through reading, through hearing, through writing, through calculating, through visuals. All those kinds of things are good for everybody. And as a believer, run for the prize. All right? Again, not because you're competing against your neighbor, you should be helping your neighbor. That doesn't mean cheating, it means helping them understand. Helping them solve and figure out how to solve something. But run as if you're running for the prize, that you want to attain the best you can do, okay, for God's glory. All right, so let's quickly review this example with housing spending that we were looking at the very end last time. So we did the example where the realtor thought the mean percentage of spending on housing in Minneapolis was less than the U.S. average. The realtor had a theory. They thought they spent less. In the new slide, the realtor doesn't know. The realtor has no idea. You got to look for words like that. No idea how much households spend in Minneapolis. Is it bigger than the average or less than the average for the country? If you're going to set this test and do this test, step one is the same for this problem. Still mu, the thing you're testing, is the mean percentage of total spending on housing for households in Minneapolis. A population parameter. You might want to emphasize that it's for all households by putting the word all in there. It is a population parameter. It's not your sample. It's not a sample statistic. This is the thing you're testing. However, when you have no idea whether spending in Minneapolis is lower or bigger than the national average, you should technically do what's called a two-tailed test. instead of putting your greater than or less than sign, you put a not equal to sign. Could be greater than, could be less than. What's the p-value calculation in that situation? We're going to still go ahead and pretend that the realtor does a simple random sample of 50 households and gets an X bar sample mean of 30.8%. That's still going to be true in this problem. But now, because it's a two-tailed test, the definition of as extreme or more extreme as what you actually observe goes two directions. In reality, the p-value could be thought of as what's the probability of X bar being less than or equal to 30.8%, which is, compared to 33, is 2.2 percentage points less than 33, or bigger than 2.2 percentage points greater than 33, or X bar being greater than or equal to would be 35.2%. I got the 35.2% in the following way. Compare these two numbers. They are 2.2 percentage points apart. Say percentage points. I'll go ahead and write, well, I probably should say percentage points. We'll leave those as percentages, but when you subtract percents, you should really call the difference a percentage point. Because it's not changing by 2.2% here. It's not changing by that amount. It's a difference. And so we don't want to emphasize that this is 2.2% less than that, because it's not. It's a difference of 2.2%, and when you do differences in percentages, you typically call them percentage points to make that distinction. So what would 33% plus 2.2 percentage points be? 35.2, and I guess I'll go ahead and write a percent there, since the difference, 35.2 minus 33 would be 2.2 percentage points. That's where that 35.2 came from. That would be just as extreme, just as far away from the null value of 33 as 30.8% is. Assuming the null is true. Yikes, that looks worse. That looks scary. Well, good news. You can find this probability using symmetry. You can just double the one-tailed p-value. Because of the symmetry under a normal curve, X bar has a sampling distribution that's approximately normal, with a mean equal to the population mean, which I'm assuming is 33%. 30.2% or 30.8% is over here. 35.2% is over there. This probability up there would be the area to the left of 30.8 plus the area to the right of 35.2. By symmetry, even though I haven't drawn it perfectly, these two areas are the same. Therefore, you can find the sum of the two areas by finding one of them and doubling it. That's good news. You can just double the one-tailed p-value. So in all these calculations, it's the same calculation except double it, multiply it by 2. Keep multiplying by 2. 2 times 0.0455, 0.0910, 0910, is that right? I think so. About a 9.1% chance of observing something, an X bar of 30.8 or less, or 35.2 or higher. Because it's a two-tailed test, you don't know which direction to go. Again, your x bar is less than 30.33. I'm not saying x bar itself was bigger than 33. Your x bar was 30.8. But when you're doing a two-tailed test, you double the one-tailed p-value. Which gives you a higher p-value, which makes it harder to reject the null. You say this is not a strong evidence. This is not less than the 5% standard that people commonly use. So by doing the two-tailed test, I have come to the point where saying, based on this problem, the way this problem is phrased, that the realtor does not have sufficient evidence to reject the null. Not statistically significant, at least at the 5% level. It is still less than 10%, so if you decided to use 10% as your boundary of very small, then you could reject it based on that. But if you use the more commonly used 5%, you would fail to reject the null. We don't have strong enough evidence that mu differs from 33. Now this might seem a little strange. Why, when doing a two-tailed test, do we fail to reject when we do the one-tailed test we did reject? In fact, some people always do a two-tailed test, even if they have a theory, one way or the other. To make it harder on themselves to reject the null, because this p-value is going to be bigger. To make it, and why is that a good idea? To make it so that they really need strong evidence before they're going to reject the null, even if they use the same 5% standard. Now again, what percent standard you use could be told you in the problem. Initially here you can always use the 5% standard if they don't tell you. But again, starting next time we'll talk about ways of deciding what standard you should use for very small in the p-value. But the big idea is the smaller the p-value is, the stronger the evidence against the null. And for this two-tailed test, because it's two-tailed, because we decided to do it that way, the p-value is not as small as it was for the one-tailed test, and we're not going to reject the null, whereas with the one-tailed test we did. Question?
At the very top on the chalkboard, it says mu equals 115. Is that, where did that come from?
Yeah, that was, I guess I was thinking of the previous example, wasn't I? Thanks. My mind was on the psychology test when I'm doing the housing spending. Thanks for pointing that out. Strange what tricks your brain plays. Let's summarize what we've learned, okay? What's the null hypothesis? The null hypothesis is a statement being tested in a test of significance. The test is designed to assess the strength of the evidence against the null hypothesis. Usually, or maybe it would be better to say oftentimes, the null hypothesis is a statement of no effect or no difference. Something has been a certain way in the past, and now you've made a change, like in a manufacturing process, for example, or in a new kind of ad for a new kind of product, and you're wondering, did something change? That's a common application. So I think perhaps instead of usually, it should be oftentimes. The null hypothesis is a statement of no effect or no difference. In the examples we've done so far, well, I guess it still could be thought of that way. The no difference is no difference from the national average. Is Minneapolis different from the national average or not? The null was the national average, and the alternative was either that it was less than, or in this case, not equal to. I'm going to go pretty fast. I will put this up on Moodle, and you could write more if you want. But I'm probably not going to give you enough time to write all this down here. If you are writing, and I do see some of you writing here. The p-value of a test. Yeah, I think it'd be better so I can go fast here to just sit and think and then write it down later if you want. The p-value of a test is computed, first of all, assuming the null hypothesis is true. I assumed that was true. That was the conditional probability thing here. And yeah, it should have been mu is 33 there. The probability of observing the test statistic, in this case x bar, as extreme or more extreme as what you actually observe, that's called the p-value of the test. The smaller the p-value, the stronger the evidence against the null hypothesis provided by the data. P-values are always probabilities, but they can often be, depending on the situation, they're often calculated in radically different ways. So it depends on the nature of the test, how you actually calculate the p-value. The Greek letter alpha is used to denote something called the level of significance of the test. The value of alpha sets the standard of strength of the evidence that will be required to reject the null hypothesis. The lower the value, the higher the standard of evidence you need, the harder it will be to reject the null for any given set of data. And the higher the value of alpha, the lower the standard of evidence. It's kind of a flip kind of thing. The easier it will be to reject the null. Okay? Setting alpha lower makes it harder to reject the null. Therefore, you need stronger evidence against the null before you're going to reject it. In effect, the value of alpha is a probability as well. It's a probability of incorrectly rejecting the null when, in fact, the null is true. This probability I calculated here, this 9.1% here, I calculated assuming the null is true. Okay, and if I do reject the null here, even though this is not less than 5%, I have a probability of making an incorrect decision of 9.1%. Because if I'm using sort of that as my standard at least, 9.1%, if that's my alpha, it would be a strange alpha to use it, but if I did use that, then this calculation would confirm the p-value is equal to alpha, and therefore it would be the probability of incorrectly rejecting the null when the null is true. Because effectively the rejection region where we reject the null, if that was alpha as well as the p-value, would be to the left of 30.8 and to the right of 35.2. Any x bar value in either one of those regions would lead to rejecting the null. At a basic level, statistically a significant event is an occurrence of an event that it was unlikely to occur by chance under a certain assumption. Therefore, an alert goes out in their minds. It's very possible something other than chance is going on here. Maybe our assumption is wrong. By assumption, I mean the null hypothesis here, really. More precisely, if a p-value is as small or smaller than alpha, we say the data are statistically significant at level alpha. Again, 5% is a common boundary to use. 5% is a common thing to use for alpha. Not set in stone. You don't have to use that in real life. But it is a common thing people often do, sort of because they don't know what else to do sometimes. Doesn't mean that's a good reason. It's just a common thing people do. If the p-value is less than alpha, you reject the null. In that case, you got statistically significant evidence against the null at the 5% level, if that's alpha. If the p-value is bigger than alpha, bigger than 5% say, then you fail to reject the null. You do not have statistically significant evidence against the null at level alpha. See a fair number of people not really paying attention. Okay, this is hard to pay attention to, hard to think about, but it's so important. Okay, you want to get this class, you got to get exactly what I'm saying here. It's going to take time. It's going to take thought. It's going to take effort. Okay, these are not easy things. This is the heart of the course, but it's also probably the hardest part of the course. It's going to take effort. But it's not going away. It's going to be with us the rest of the semester. These terms, these ideas, in different situations. Here's a summary of what to do to calculate p-values based on what's called the one-sample z-statistic. You don't have to actually calculate in the steps that I did here. You can first calculate z based on x bar, based on this formula up here, and then calculate these probabilities for a right-tailed test, left-tailed test, or a two-tailed test. That's another common way to do it. It's a little different than the way I did it on the board. Calculate z first, sort of separately, is the idea there. Here I was calculating z within the probability notation, going from here to here to here. You could calculate this negative 1.69 separately, and then just do this probability calculation right here. That's the gist of this table. All right, for the rest of the day today, let's get back to simulation. Rod Carew, there's just one more day with Rod Carew here, I think. And the simulation we're going to do today is pretty tricky. You want to pay attention, write stuff down, and maybe watch the video. First thing I'll do, I've already shown you. I'm going to use equals binom dist to calculate the probability distribution for his number of hits. But this time we're going to do 4 at-bats instead of 5. I think 4 official at-bats in a game is maybe a little bit more common than 5. So we're going to assume he's going to get 4 at-bats per game here. Remember how the syntax goes? You first put the value of x that you're thinking about. That's called k. This first one's in cell B5. Then you put the number of trials n. That's in cell B2. We need dollar signs because that's a fixed cell reference. Zoom in with the camera there. Then you need the probability of success on any one trial. That was the 0.388 in cell B1. And for the probability that x equals k, you put false for the cumulative spot. I can also calculate cumulative probabilities. Binom dist, the k value, the n value, the p value, probability of success, but then a true instead of false. This calculates cumulative probabilities. Let me round all these numbers to 3 places after the decimal, which I can do by highlighting them all and going up here to decrease decimal places, until I get 3 places after the decimal. What I'm about to do is I'm going to simulate for 162 games, which is how many games there are in a season. 162 games. How many games there are in a season? I'm going to simulate the final results of each game as either 0 hits, 1 hit, 2 hits, or 3 hits, or 4 hits. How am I going to do that? I'm going to use rand between 1 to 1,000, which generates a random whole number between 1 and 1,000. We've done that before. Copy and paste that down. Click and drag. 162 games. And then in the next column, I'm going to do something pretty tricky. So listen carefully. Based on the result of rand between, and based on this probability distribution here, especially the cumulative one, I'm going to decide whether he got 0 hits, 1 hit, 2 hits, 3 hits, or 4 hits that game. Based on this cumulative probability distribution here, if rand between is between 1 and 140, I'll use RB to be an abbreviation for rand between. If it's between 1 and 140, that's going to correspond to 0 hits. Why? Because the probability of 0 or fewer hits is 0.14. And rand between 1 to 1,000 is 1,000 numbers. The first 140 of them are 14%. On the other hand, this is the number of hits. If rand between is between 141 and 496, that's going to represent he's getting 1 hit. There's a 0.496 probability that he will either go 0 for 4 or 1 for 4. He gets 1 or fewer hits. Getting 1 hit exactly is 0.356, which is the difference, 356 between these when you count one endpoint. The actual difference here is 395, but since you're including 141 in your whole number count, you have to add 1 to it. Use the 0.496 there as this right boundary. For the next one, 497 to, look right here, 834, that's going to correspond to his getting 2 hits in a game, $835 to 977 is going to correspond to getting 3. 978 to 1,000 is going to correspond to his getting 4 hits. And that's going to match the probability. So that's what we're going to do here. Except to do this, to count the range-betweens correctly, you have to use an if statement multiple times. And this is the most confusing part. I think for the sake of time, I'm just going to type it, and you can just retype what you write or re-watch here. You can think about it on your own after class. We'll probably talk about it more next time, but I do want to get to show you Adrian Peterson's output here. So I'm just going to type it quick. These ran-between outputs are G5 through G166. I'll put a comma 0, then a comma if. I'm going to use multiple ifs here. I guess I'm not explaining really at all, and this is going to be so confusing because of that. And that's hard to see too, isn't it? This is not turning out as well as I was hoping because I was hoping I'd have more time. Okay, that crazy looking thing just summarizing real quick, is going to return 0 if your number, you know what, I'm doing this, let's see. It's going to return, I'm doing it wrong. I want just G5, not G5, sorry. Maybe we'll just have to do Adrian Peterson next time, unfortunately. Hang with me here. Okay, if this number is, I'm whipping this up too. I'm trying to do this too fast.
Slow down.
Slow it down. We got time, we got 2 minutes. If this number is less than or equal to, look on the board, 140, then return 0 hits. Otherwise, if it's not less than 140, you're going to do this. If the next one, so now you're in the case where it's not less than 140. If it is less than or equal to 496, and also by assumption greater than 140, then you return 1 hit. I was too ambitious here, I think. Else, if it's less than or equal to 834, then return 2 hits. This is so bad without explanation, isn't it? Else, if it's less than or equal to 977, return 3 hits. Otherwise, if it's bigger than 977, you're going to return 4 hits. Probably, you might have no idea what I'm talking about there. I am trying to follow what I have on the board there. The if statements combined in a nested way like this allows me to do that. If this number is less than or equal to 140, it's going to correspond to his getting 0 hits. If it's less than or equal to 496, it's going to correspond to his getting 1 hit. If it's less than or equal to 834, and again the assumption is it's greater than 496, for example, you're going to get 2 hits. If it's less than or equal to 977, you're going to get 3 hits. I wanted more time to explain that more. Let's just see the result. With this game, he got 2 hits because ran between was 725, which is in this category here. Hang with me 1 minute here still. Do this for all the games. I do want you to do this for the assignment still, even if you don't understand what you're doing. Do it for all the games. Oh, come on. Do it for all the games. And then use equals count if over here in a way that I think I'm going to have to make a separate video for you to show you the details. I'm going to make a separate video this afternoon where I explain this more slowly and show you how to finish it as well. It's just too ambitious. Okay? I'll do it in a separate video. I still do want you to do this as part of the assignment.